Hello, this is Physics 1020 and 1090, lecture for Friday, March 20th. We're now in Chapter 25, Optical Instruments, and this is the first video from the Friday lecture. I'm going to talk about microscopes. We're going to look at what's called the compound microscope. And a compound microscope is a two-lens system. That is, it has an objective lens, which is put right near the sample, and it has an eyepiece, which you look through with your eye. So we have a two-lens system. We have to see how we handle the situation when you have two lenses. So here's a little more schematic of what we have. We're going to analyze a case where we have an object that's 2.5 centimeters from the objective lens. The objective lens has a focal length of 2 centimeters. The objective is 12 centimeters from an eyepiece. Both of these are converging lenses. The eyepiece has a focal length of 3 centimeters. And what we want to do is we want to find the final image. Okay, how do you do this? Well, it's a two-step process. First, you're going to take your object and you're going to find the image produced by the first lens, ignoring the presence of the second lens at all. And then when you get that image, you're going to use that image, the first image, as the second object, and you're going to assume that was the object and find the image it forms by the second lens, the eyepiece. So let's start with that first step of finding the image produced by this object and just the first lens. So I've removed the second lens completely from my drawing, and I just have my object and the first lens with a focal length of 2. And you can see this now. Let's first just analyze it using our rays. This is a good review of how to handle rays through a lens. We're going to start with our 3 rays. There's one ray that comes across horizontally and then goes down through the focal point and on downward. There's going to be another ray which starts at the object and goes through the focal point and then out horizontally. So one horizontal, then through the focal point, one through the focal point, then horizontal. And finally, there's going to be a third ray, which is going to go through the center of the lens, and that ray is undeflected. And they all come down and they meet right here. So there we found our image. This is, you can think of this as object 1 and image 1. So we found the image produced by the first lens of the object. Okay, we did that using our 3 rays. That was good. Now let's do it analytically. So same picture, but now we're going to analyze it analytically. We have our thin lens equation. 1 over f, 1 over focal length is equal 1 over the object distance plus 1 over the image distance. Our focal length is 2 centimeters, so you get 1/2 equals our image distance we said was 2.5. So you get 1 over 2.5 plus, and this is the object distance, and then plus 1 over the image distance. Okay, 1/2 is 0.5. 1 over 2.5 is 0.4, and we bring it to the other side of the equation. We get 1/2 minus 0.4 equals 1 over the image distance. Well, 0.5 minus 0.4 is 0.1, and then we get the 0.1, and we take the reciprocal, and we get 10 centimeters. And that looks about right, because the focal length is from here to this dot here, the focal point. If that's 2, then 2, 4, 6, 8, 10. This looks like about 10. So it looks consistent. How about the magnification? How did we get that? Well, remember, the magnification is minus, and then you have image distance over object distance. The image distance we found as 10 centimeters. The object was originally 2.5 centimeters. 10 over 2.5 is 4, plus the minus sign. Your magnification is minus 4. What you have here is a real inverted magnified image coming from the object. Now we're going to put in that second lens. let's remember here, the image distance we said was 10 centimeters. That's what we calculated just a second ago. But the distance from one lens to the other was 12 centimeters. So if you have 12 centimeters here and 10 centimeters here, that means this distance is 2 centimeters. 12 minus 10 is 2. So what we have now is we're going to take this, which is our image 1, and call that the object 2, the second object. And that's going to become the object for this lens. So what we have is a problem where you have a object 2 centimeters from an eyepiece which had a focal length of 3 centimeters. What is the image that it produces? I had to get a little bit larger paper. Sometimes these drawings get large. Okay, so here's our new object. It's the first image, so it's our second object. It's 2 centimeters away from the lens, which is 3 centimeter focal length. So we have 3 rays. We have 1 ray. It's coming in parallel, and then it goes through the focal point over on this side and out. Then we have another ray that looks like it's coming from this focal point. Comes down and hits this lens, and it goes out parallel. And the third ray is the ray that goes through the lens at the center, undeflected, and on up. And those rays, they're all diverging apart, so we're not going to ever form an image over here. They're all spreading out. They're never going to all meet. But if we back extrapolate them, we see that all those rays come out and meet about right here and form an image, a very large image, which is why I had to make my paper so large. So your image 2, or final image, is large. It's a virtual image, and it's going to be inverted. Let's calculate this one analytically, just to remind ourselves how it's done. We have 1 over the focal length is 1 over the object distance plus 1 over the image distance. The focal length was 3 centimeters. The object distance we had found was 2 centimeters, 1/3 minus 1/2. Well, put it over common denominators. We have 2/6 minus 3/6, or a minus 1/6. Take the reciprocal. You have a image distance of minus 6 centimeters. So the final image, image 2, is 6 centimeters from the eyepiece. It's negative, it's virtual, it's inverted, and it is magnified. The magnification is minus 6 over 2, or in other words, 3. They were both inverted, so the magnification is positive because one's inverted, the other one's inverted, so it doesn't flip. So you have a magnification 2 is 3. Let's put all this together. You now have your original object, went through the objective, formed an intermediate image, which was then used as the object for the second lens, and we got this large image, final image. It's virtual, it's inverted, and it's magnified. Now, what's its magnification? To find the total magnification of a 2-lens system, you take the magnification of the first lens and you multiply, not add, multiply by the magnification of the second lens. The magnification of the first lens was -4, the magnification of the second lens was 3, so the total magnification is -12, as it should be because the final image is inverted compared to the object, so it should be a negative number. But it's highly magnified because its absolute value is 12, which is much larger than 1, so we get a very large magnification. So this is the compound microscope. You know, you can think about a compound microscope this way. This first lens here, where the object is just outside the focal point, acts like what I call the slide projector, where you project the image up on a screen. And then the second lens, the eyepiece, acts like a magnifying glass, where you put that image, intermediate image, inside the focal point, and you get to use a magnifying glass. So it's a compound microscope is kind of like casting your image up on a screen using a slide projector, and then walking up to it with a microscope, a magnifying glass, and looking and getting a very, very high magnification. That's the compound microscope, a classic example of a two-lens system.